So hello everybody, also warm welcome from my side, and I'm trying to entertain you for the next 45 minutes, so I usually fail miserably in entertaining you. And I mean, it starts with the title, Resilient Functional Service Design. How strange is that? But I'll try to explain that to you in the next 45 minutes. And if you're still confused after the talk, I did something wrong, and then do that with the evaluations, and we'll see. My name is Uwe Friedrichsen, and don't want to waste a lot of time with introducing myself or my company. Yeah, that's Codecentric, blah, blah. That's enough of advertisement, and let's get into the topic. So first, a little reminder about what's that resilient thing. Just this very brief introduction in 2 minutes. So we create software to create some business value. That's the reason why we are doing that. I mean, for our after-work projects, might also be fun or something like that, but as long as we're doing that for earning money, usually that's for achieving some business value, so making the customer happy or make money for the company or both of that in the best case. But that only works if software runs in production. So in test or development, it doesn't make any money, and customers are also not made happy by stuff which you have in development. But that's not enough, because software also needs to be available, so runs according to the specification. Being there, being responsive, not being latent, giving the right answers, and so on. Because as soon as the software is no longer available in production, which also includes latency, by the way, that means that our customers are no longer satisfied and that we're not making any money, usually. And probably in the long term, we will also lose a lot of my customers and so on. Yeah, and we have a lot of measures around there for many years, how to make things highly available. But what's the problem these days? Problem is quite straightforward. We're dealing with distributed systems, and distributed systems rewrite the rules how you make systems robust. So just throwing a lot of expensive infrastructure and hardware on that isn't enough anymore, because there are so many sources that can screw up the availability of your application, which is not on your machine, but somewhere out there where you reach out to, that you cannot plan for that, and that infrastructure is not going to help you. So Leslie Lamport said then, okay, a distributed system is a system where a computer that you didn't even know that it exists can render your own computer useless. So, which is basically summing up the problems of distributed systems in a nutshell. So today, failures in our highly interconnected, distributed, and complex system landscapes are no longer avoidable upfront by throwing infrastructure, hardware, anything on that. So they will happen, and they're not predictable, and they're the normal case. So, and yeah, it's also going to get worse, which is, we're running on cloud-based systems, so nice, perfect resource provisioning model, but no high availability hardware and resources there. And microservices, so welcome to microXchg, distributed by default. While the customers are expecting even more availability, so zero downtime is the word around there. And mobile IoT multiplying the number of involved peers on unreliable network connections. And social media, which gives you completely unpredictable load patterns. So nothing's going on your server, whoop, peak up, and oops. And so ever increasing complexity and challenges and more connectivity that you have to deal with. So in the end, don't try to avoid failures up front, embrace them. And that's basically what resilience is about. Okay, so much for the reminder. Now you say, okay, I accept that, and I want to dive deeper into that. And I try to learn how to do resilience. And there's a trap in there. First, you start to read a few articles. Here's the circuit breaker, here's something else, and blah, blah. And so let's do a training or something like that. Let's assume you do the mistake and do training with me. And then you will first find some kind of taxonomy, which I use to organize all these ideas, concepts, and patterns a little bit. So these core decisions that you have to make up front, And then how to detect errors at runtime, how to recover from them, how to mitigate them if you cannot recover immediately, how to treat the original faults, how to prevent errors from occurring, so reducing the probabilities that errors will occur, and some complementing patterns which makes all the other stuff easier. Okay, and then I talk about all that stuff, and woo, a lot of stuff shows up. Usually I'm not going to introduce all of that because that's killing people even if I do a one-day workshop. Yeah. And then you try to digest that stuff. And the observation I quite often have is something like that. So if we take all that and it start up these core decisions, whoa, that's this theoretical blah blah. That's a little bit uncool. We know that for eons anyway, so go on, and where's the interesting stuff? And then we go to these recovery and detection patterns. Yeah, now we're talking. That's cool stuff. And hey, there are also library support. And can't we just turn that into more, don't you have more code? And can't we just turn that old workshop into a coding session or something like that? And with the mitigation patterns is, more cool stuff. And aren't there any more libraries like Hystrix and so on that we can just plug in with one line in our Maven configuration or something like that? Yeah, we want to do more of that. And then I come to this fault treatments. Oh, yeah, that's one off. Yeah. Next one. So prevention pattern. Whoa. That sounds a little bit nasty. That's not that easy like the other stuff. So not immediately coding and hard of lot. We'll come back to that later. And the complementing, yeah, that's okay. We'll pick them up whenever we need them. So it's basically like that. And there's a problem in there. Because here, the priorities, as I showed, cool stuff. It would be a little bit larger, the last one, than the second last one. The problem is relevance for the robustness, the resilience of the application is like that. Down there, I think it's a little bit more important than most people think that those patterns are. Well, that's okay-ish. Yeah, works nicely. Those ones are a little bit overestimated, from my opinion. But here's the problem. These are really important for making your application robust, resilient at runtime. And there are two more claims I have. So first one is, if you don't get this part right, all the other stuff won't help you at all. And the second one is, that's really complicated stuff. That's brain-twisting stuff. That's not easy. That's not just one line of a configuration, a little bit of hacking. That's real brain power. And if those two claims are true, we might have a problem, actually. So I'll try to prove them and show some not so easy ways out. So these core parts are really relevant, I say. What are they about? Usually I talk first about isolation. Isolation is that idea that the systems must not fail as a whole, and therefore what we're doing is we try to split that up into several pieces and isolate them against each other so that we don't have any cascading failures, which means, okay, if one piece over there has a problem, that it drags down the next piece so that the errors is going to spread throughout the different pieces of the system. You can translate for this conference a piece with microservice or with self-contained system or however you like. That's basically what we're talking about. Yeah, and you say, yeah, sure. Next one. I'll talk about the bulkhead pattern. Some people, I heard sometimes that people think that's about confinement of thread pools because there are some not so well examples or not so well picked examples in the Michael Nygaard book and in the Hystrix wiki documentation, which is about bulkhead pattern, but it's just a specific sample how to implement that. So basically bulkhead pattern means implement isolation. Period. So find your pieces and isolate them against each other. And you might say, yeah, and I wrote something like, that's extremely hard. And you might say, what the heck is he talking about? I slice pieces all day. I do that for many years. I slice my software. Where's the problem? Heck, the problem's here. How can you avoid this situation? The situation which means you have a service B which needs to give a reply to service A for enabling service A to answer the client request, the original request. So as soon, and that's on a functional level, so business logic level. So as soon as service B is down, service A can no longer give a proper response, because that is broken isolation by default. It doesn't matter how many circuit breakers or stuff you have in between. If you're dependent on a functional level, you're toast if the other service is down. So all the technical stuff doesn't matter. And how can you avoid this situation, which you see quite often, also that you have long change of dependencies which build up then, that you split up your functionalities in many parts, and just to fulfill one client request that you have to call a lot of services, so make up a long activation path until you're able to answer that request. Because this is a problem with availability by default, because the availabilities of all these pieces multiply up, and availability is a number between 0 and 1. And numbers between 0 and 1, if you multiply them up, they become smaller and smaller and smaller and smaller. And if you have a lot of these pieces, you're in trouble. Okay, without ending up with something like that, because you say, ooh, all that stuff is killing me in production, so let's drag all these pieces together, let's create higher cohesion, and in the end you end up with a mothership service, which we can also call a monolith, basically, which again violates the idea of isolation, because isolation says split these pieces apart and isolate them together. There's nothing to split apart. But you say, stop, stop, stop. We know how to split things up. We learned these design things for a long time. So here are our best practices. In the beginning, when we started studying computer science, we learned all this divide and conquer, so functional decomposition stuff. But we are smarter than that by now, because if your developers say, I learned, don't repeat yourself, dry, 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 be dry. I mean, I was quite long in the agile community around, and every second sentence I had the feeling you heard Yagni or dry or emergent, which is, yeah. Okay, but dry. Or if you're more like an architect, you say, I design for reusability, the holy grail of architecture for 20 and more years with distributed approaches, which never worked out, actually. Or layered architecture. I mean, whenever you come to a company for the last 20 years, say, show me your architecture. It's like whoop, whoop, whoop. And this repeats also in the distributed level. Whoop, whoop, whoop. Yeah, okay. Or maybe you're very agile and you say, I do TDD, or I use emergent architecture, anything like that. But that means nothing. Like, in the end, all that stuff that is hardwired in your brain will show up in your architecture, because you will do also all these things, because that's the way how you're biased, how your brain's wired. Unfortunately, all these great ideas, which have a place where they're absolutely valid, don't get me wrong, tend to lead to this stuff. I mean, this is dry, this is designed for reusability, actually, and to this stuff, that is layered architecture, that's functional decomposition. And so you end up with this high coupling, low cohesion, so the opposite of what you try to achieve, actually. So highly coupled, tightly coupled systems, and because that kills you at runtime, then you probably start again with all this stuff to drag more cohesion into the pieces, and you have the monolith again. So yeah, welcome to distributed hell. It's not that easy. But we still have one band-aid in place. Caches to the rescue, isn't it? Whenever things don't work, use a cache. So, I mean, the idea is nice. Who the heck did that animation in there? Or forgot to take it out? Okay. You say, yeah, I know I have this tight dependency to service B, so I just cache its data or responses over there in service A, and whenever service B is not available, I can still give you a response. I mean, I accept that the data might be a little bit stale, but that's it. Yeah. Really? Is it that easy? Is that the one fix for everything? So, or let's phrase that a little bit differently. Do you really think that copying stale data around your system is a suitable measure to fix an inherently broken design? I don't think so, to be honest. I mean, don't get me wrong. Caches are a great thing, and you need caches in distributed systems. But they are not a fix for a broken design. If you use it this way, you will end up having lots and lots and lots of caches. You have to have lots of stale data. You will have lots of consistency issues. And you will have to transport all that stuff around on the wire. And if you think about the fallacies of Peter Deutsch, about fallacies of networking or distributed systems, bandwidth is infinite? No. And even within one data center, there are limits of bandwidth. And if you go across data center boundaries, there are really limits of network bandwidth. So, yeah, okay, the fix is gone. And we figure out, dear, we probably have more or less to relearn all the stuff, how we design systems, how we split up that stuff for distributed systems. Because all this other stuff works well inside a process. Layered architecture inside a process is okay. Functional decomposition is okay. Don't repeat yourself. All this reusability stuff is perfectly fine within a process if you do that nicely and right. But across process boundaries, you really have a problem with that. So you probably say, oh, okay, give me the cure. So where's that 3-bullet point plan, how to fix that? Because you said that, you must have the cure for that. And yeah, sure, here's my cure. Here's one size fits all, work out of the box in all contexts, just add water and steer, 3-bullet point panacea for designing perfect bulkheads. Okay, you sense a little bit of irony in there, probably. And yeah, sure, there is some irony in here, but it's also it's sort of serious. So here's my 3-bullet point plan, which starts with, you need lots of those brains, but please, no Walking Dead or something like that. Inside living human bodies, heads, and working. So that's important in here. And then you probably need some of those. So whatever you use to visualize your design ideas and play around with them. You can also use your computer and your favorite drawing tool or whatever. But it's not about tooling. It's about how can you visualize things best. And then it's a lot of hard work. Sorry about that. So no line of configuration to drag into your code. It's hard work. You really have to understand the business, how it works, how the organization works. And you'd have to try to figure out what's essential functionality and what's just grown habits in this organization and what's just cargo cults and so which are going on there. So to figure out, because all this stuff usually obscures the real functionality, and then you have to try to figure out how this all splits up and works and repeat and repeat and repeat, because you have a lot of forces around there which make it hard. And you won't find a silver bullet. And just by seeing that this 3-bullet point plan turned out to be a 4-bullet point plan, you see it's not perfect. So there is no perfect solution for that. But still, I would like to offer you a few guiding thoughts about that stuff. So the point of work where I am at the moment. I think there's still a lot of ground to be covered in this area, and we suck quite a lot with that for 20, 30, 40 years, how to do that right. And I also, as you've seen before, I don't have the perfect solution, but I try to get better in that step by step by step. And if you have a great idea, just add it, share it to the community, and maybe we all together will learn how to do these things right. Here are my ideas. Not complete, not perfect. What I've seen is we are sent back to the foundations of good design. And the foundations are not these design principles that I've shown before. These two ones. High cohesion, low coupling, and separation of concerns. And you say, yeah, I know what that is, so what's the deal? And the problem is, what I've seen, almost 100% of the people, including me, is we exactly know what that is. And we have no clue how to do that. And that's a big difference, knowing what something is and being able to apply that. So that's really, really hard. Figuring out good separation of concerns, figuring out slices between your functionality that give you high cohesion and low coupling. And within a process boundary, you will usually never figure out, because otherwise monoliths would look differently and not end up being all these big balls of mud or spaghetti code that you usually find when you look into a monolith which is older than 2 years, or in agile communities older than 6 months, usually. So again, don't get me wrong, agile is important and it's the way you have to go, but if you only focus on being fast and pushing out business features without thinking about any qualities in there, you've got a problem very soon. You end up in these refactoring sprints, which means I throw away my code and rewrite it in a proper fashion, which is not refactoring, but is rewriting sprints, more or less. Okay. And as I said before, that's crucial process boundaries, and it's very poorly understood issue still. And I usually prove that. I say, the best paper about how to apply separations of concern, how to implement that I know, and I've read quite a lot of papers meanwhile, is a paper from David Parnas on the criteria of decomposing pieces or systems into modules or something like that. And the paper is from 1972. That's quite a while. And we haven't learned a lot since about how to do these things. He showed some heuristics how to do that. And Jim Coplien repeated that in his Lean Architecture book, and we have, meanwhile, domain-driven design, which is also a great thing. Unfortunately, most often not properly understood. So again, this problem, knowing what the patterns mean doesn't mean that you're able to apply them, how to apply them. So I'm an examiner for some architectural certification, and usually the participants get some kind of case study and then have to answer some architectural questions about that. One of these questions is usually do a functional design, also high-level design for this case study. And then at least 50% of the participants usually say, and I apply the DDD principles on that, so the DDD patterns. And then the next figure is then their design, and I say, oh, okay, that's interesting, but that's not DDD, that's something different. So I quite often call that then EDD, so entity-driven design, which is not actually domain-driven design. So there's a lot of problems in there still, so we still have to learn that. Here are some ideas about that. First recommendation is try to understand your organizational boundaries. Because the organizational boundaries, if you look not into your organizational structure, but your operational structure. So for the Germans here, not Aufbauorganisation, but Ablauforganisation. Because this kind of organization tends to have low coupling and high cohesion already in it. And so you can quite often figure out where are these business domains? Because these organizations tried to optimize that for many years, and that's the stuff, how it works. Not what the org chart looks like. That's something different. That's politics. Don't look at that. Look at on the operational structure, how that works. And then try to understand your use cases and flows, because a good slicing functionality is in the behavior, not in the structure of the system. So it's not in the static parts, it's in the dynamic parts. because what makes your life hard is the dynamics. So if you have to go for fulfilling one use case, you have to call 40 services, you've got a problem. So try to make sure that you understand what your flows are, what your use cases are, because then you can test your design against it and figure out, oh, this use case needs to go through needs to access 20 services. Probably I've got a problem here, so I might need to revisit my design to get that better. Or maybe even packing use cases into ones. It depends on your domain, but it helps you to understand what's going on. And then, yeah, we have that DDD. Sometimes it also helps to find areas which change independently from each other. So if something changes here, it's not affected. Oh, yeah, that can also help me. And as I said before with this short idea about domain-driven design, don't start with the data model. It's not in the static model. The magic is in the dynamic model, in the functionality, in the behavior. That's where you need to start with. That's where you find your high cohesion and low coupling, and that's where you find your separation of concerns. And we are so much used to write class models and component models, and so if you still use something like UML, I mean, yeah, you would never admit that publicly, but it's okay. So if you're using something like that, or if you read something like that, how often do you see a class diagram or a component diagram? And how often do you really see a collaboration diagram or something else, an activity diagram? And you will figure out that in 90% of the time, you only see the static diagrams, and very rarely you see some dynamic diagrams. And that's this problem, that we all tend to start with the static parts because they're easier to grasp, but the magic is in the dynamic parts. Second point is short activation paths. So activation paths, as I briefly mentioned before, the number of internal remote calls that you have to do, so this graph that you span up to fulfill one request. And if they're really long, you run into a problem because it compromises availability. It's like that big tree that I've shown before when I sketched the problems. And it increases latency if you have synchronous communication. It also increases latency if you have asynchronous communication, as long as your peer is waiting for a response. And it increases the likelihood of failures. So what you try to do is you try to minimize the amount of remote calls that you need internally to satisfy one request. And this gives you, and now you're in the area of architecture, where it's only options and trade-offs, and no black and white, and no 1 and 0, but always some problems in between, because it gives you opposing forces. On the one hand, you try to implement that isolation thing. Avoid the monoliths. Try to get a clear separation of concerns, so split that pieces up. On the other hand, you try to minimize the number of remote requests per external request, which says, cram everything into one thing. And this is an imposing force which you need to balance somehow. And here you see, caches may sometimes help, not a general band-aid sometimes, but you have to deal with the stale data in there. So you avoid one trouble for running into another trouble. That's what we call a trade-off in architecture. Yeah, that's so choosing the way how you want to die. That's basically, so what's worse? Yeah. And the last one, probably quite important to understand with distributed system, forget about reusability. This dear-held holy grail of architecture. We have to reuse everything because that's our business case. We build reusable distributed assets, and they're reused so often that this makes the whole development a lot cheaper. So buy this expensive ESB, buy this expensive core, buy this expensive application server, buy this expensive whatever. Because after this initial investments, by reuse, we get all the money back. And it never worked. And it will never work, by the way. So the Holy Grail is broken, this argumentation, and I also talk about why it's broken. But first of all, reuse means coupling. Reuse means you need to be able to access that piece of code for doing your work. That's reuse. So usually it leads to very bad service design. It leads exactly to the things that you've seen before where I said that's the problem that we have, that B always needs to be there for A to be working, or that you get all these large trees. I mean, part of the story why Zoar, the original way of Zoar, died 10 years ago is that they started with that reuse thing, and it came up with these layered architectures thing and all that crap. And I've seen some of these reuse statistics. If you Google for them now, it's quite interesting. The original articles we said, yeah, reuse is the big thing, are still there, and the statistics are gone. But I've seen them back then in 2005, 2006, some statistics from companies, and the typical reuse factor was 1.1 or 1.2 or something like that for the really good ones. So 1 is it's used once, the service. 1.1 is, yeah, it's used a little bit more than 1. So that was the average reuse factor. And I think that this 0.1 or 0.2 was mostly triggered by the log service. And so, yeah. So it compresses availability, and it rarely pays. So it's not even hard to get good reuse. It's really expensive to implement good reuse. Because Fred Brooks already said in the early 70s in one of his famous articles, there's a rule of 9. So turning a project asset into a reusable thing, into a reusable component, is a factor of 9. So 9 times the effort. Factor of 3 for finding the right interface, to finding the right abstraction that you offer to the outside. If you all remember these discussions about REST interfaces, that they have to be backward compatible over time, that you better should not use versioning and so on. This means that you have it's hard thinking to figure out a good interface model. Not just exposing your internal model, but an interface model, how it's used, how it's accessed. Also the data model of the interface. It's really hard to figure out. That's a factor of 3 for finding the right abstractions, that it's generally usable and that you have the right abstraction. And then the other factor of 3 is making that production ready, that piece. So thoroughly test, and not just a few tests over here, yeah, it works right in my context, but for all the other contexts, maybe some documentation, some hardening, all that stuff, which gives you a factor of 9. But let's say we are smarter than in the 70s, so let's just take a factor of 5, which still means that you need to reuse this asset at least 5 times, that it's worth the effort to turn one project asset into a reusable piece of code. Otherwise, your business case is broken. And usually that's the reason why all that SOA stuff failed miserably in all that stuff before, and Corba and whatever we had. There were other reasons, but that was one of those reasons. So reuse rarely pays. Be really careful. Usually, I recommend do not strive for reuse, strive for replaceability, because this gives you this kind of isolation that you say, I will be able to throw away my code inside if I figure out that this code sucks and replace it by a new implementation, without changing the interface, because this gives you, pushes you toward this separation of concerns and this low coupling and high cohesion thing. There's this idea of replaceability in your head. That's the right direction to go into. And if there is an asset or service, we're at the microXchg, so the microservice, which is really worth to be made reusable, it will show up over time. You will see, oh, I need it 3 or 4 or 5 times. Now let's turn that into a reusable asset. But before, forget about that. So these are the basic ideas that I have to offer about bulkhead design and how to create these things. Hopefully a little bit better. As I said, not perfect, not complete, a lot of ground still to be covered. And then, one more thing that's quite often forgotten, which gives you a lot more options, just to add that. That's this other part down here. Communication paradigms. I've seen so many projects we started up and said, yeah, we're doing something new. I'm around quite often in the Java area. So yeah, we use that Spring Boot and REST interfaces, and that's done. And now let's start to think about the functionality. I mean, there's nothing wrong about Spring Boot. There's nothing wrong about REST. Both are, it's a great technology, it's a great style. But if you decide before you know what you're going to do, you give up some options. And I show you here. So communication, you have several options. Synchronous request response, which is HTTP and also REST. I mean, quite often people say they're doing REST and actually are doing HTTP, but that's out of scope here. And or messaging in a command style or in event-driven style or in other style. And it influences this original slide from my workshop, so it was the patterns and so on. But there's this third bullet point. It also heavily influences the functional bulkhead design. And that's very often underestimated, because here's the idea. If I go with synchronous request response, I tend to take the path of a functional decomposition of my functionality. So I have this starting point, this top-level service, and this one calls another service, which in turn calls another service. This comes back, then there's another service call. So call stack implementation. The way how we slice up the functionality inside a process. It's one way. So you see, I call that horizontal slicing because you can draw horizontal lines between the layers that you create by that. So, or the levels that you create by that. Asynchronous communication, no matter if you use messaging or events, I just used the eventing here, tends to create a vertical slicing, go with the flow. I do some piece of, I do a little bit of work and then I finish up and I tell the next one to take over and then, or I send an event and the next one listens to that and takes over and I tell the next one, tap, 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 until eventually all the work is done. So it's a different way of slicing. And it's not only that, there are some more effects in there. So decomposition I mentioned, coordination. So you end up with different styles of coordination. In the one time, in the synchronous way, you usually have the coordination logic in the services, and you tend to use orchestration for that. So you look for these orchestration engines, a centrally controlled approach. The other one is usually event chains and choreography, so decentralized, no central control in there, but the way how they respond to the events controls how the big picture looks like. So more like a society than just a dictatorship or something. So it's a different way. Transactions, internal, external, error handling, internal, external, different ways usually. Separation of concerns. I personally think that in many cases, the asynchronous way helps you to get better for towards single responsibilities, because in the other ones, you still have to build in the error handling, the transaction handling, the coordination of the service, and all that stuff blends into one service. So you have several concerns mixed up, so business logic and a lot of the other features. Encapsulation, yeah. The first one drives you more towards reusability because you reuse that piece of code. And the other one, it's more towards replaceability. But there are still, depending on your business case, this can be also the other way around. It's just a bias. It's not a rule or something like that. And in terms of complexity, it's a draw. Because this functional decomposition is easier to grasp for the brain, but so it's easier to understand on the high level, but the services are more complicated. The other ones is hard to grasp on this coordination on the high level, but the services themselves are easier to understand usually. So again, choose your death. So it really influences these functional service design a lot. You will end up with a lot of different designs depending on the communication paradigm that you use. And I use that also in my workshop. That's a simple case study that I use and let the participants then do a design. So the participants of my workshop from yesterday still try to recover from that. So that's therefore there in the other talk. They're fed up with me. And I usually, in a former version, I started with a simple version of order fulfillment. So this piece of code that you need to write between the customer pushes the button buy now until a warehouse system or a digital asset delivery system takes over. So payment and preparations and so on. And say start with something simple, just simple order, only credit card payment, non-digital items or normal warehouse system. And then all this customer retention stuff to be added into it and different payment types and different types of assets that could be delivered. And I give them then this task and said, try to create a bulkhead design. I split the people up into different teams and say, one team should use synchronous request response, next one asynchronous messaging, the next one eventing. And let's compare the designs. And that's very interesting what's coming out of that. So I've sketched here 2 example solutions. So yeah, it's basically here all the external systems are given, fill out this piece. And with synchronous request response, it could look like that. So it looks quite straightforward. Here's the customer who pushes the button, and then here's the central order fulfillment service, which first goes over to payment service and then to the shipment service, and then the payment service uses either directly contacts the external systems, or for payment, it contacts the account service, which goes to the accounts receivable system, or otherwise it contacts the payment providers service, which then goes out to the different payment providers. And same thing over here. And in there, you see there's all this loyalty system handling, the promotion handling, the coordination logic, including the transaction logic, and error handling, and the coupon logic, and so on. So easy to understand and from this high-level view, but quite complex services internally. On the other hand, if you go for event-driven design as an example, this could look like that. So you start up over there, and then you have one event that some services which do just one piece of logic pick up, and then if they eventually complete, some other services here pick up, and this assets library services, they still do a notification for email service, and it's not about if that design is perfect or not. I created a design, so per definition it's not perfect, but it's, okay-ish in best case. But it looks very differently. You end up with very different service designs. So it gives you different options. And my key point here is, do not limit your design options with upfront decisions that you do not need to make. So you do not need to say, before you even understand the first functional requirements, I use REST or something like that. Again, REST is a great option in many places, but it's not the right option per se. There can be use cases where the other options fill in a lot better. And for instance, this order fulfillment is a lot better to be implemented with an asynchronous style, not with a synchronous style. There might be other places, or like Fred said yesterday in his, when we had the meetup, he's doing a lot of work in recommendation services. An asynchronous style is just perfect there. So the synchronous style is, you can use that if you really want to, not so good. That's basically the ideas I want to share. Just to wrap up, we need resilient software design. I hope we agree on that in today's system landscape. If not, come along, have a coffee with me, and I explain that in detail later on. Bulkhead design, crucial for robustness. Often underestimated, still poorly understood, massively underrated, and it's very different from the traditional way we have learned how to design systems. So we have really to reset our brains, unlearn this old stuff, and relearn the new stuff. And the communication paradigms broaden your design options. And if this was, again, all way too much that I crammed into one single talk, then just try to remember that one sentence. We have to relearn design for distributed systems. That's what I had for you. Thanks a lot for your time and your patience. Now we have time for questions.
So, questions?
Does anybody dare to ask a question? Ah, yeah. Here are the brave ones.
There are some other opinions of people saying simply doing distributed system is simply placing the caches at the right place. So you should design your caches. This starts at the Intel CPU and goes over Akamai if you are on the web or on your Redis internal caches and goes into the HTML5 storage of your browser. So reducing the traffic by 95% is possible. I've seen such examples. What is your opinion on that?
As I said, I hope you didn't get me wrong with that. I never wanted to say that caches are a bad idea. You need caches in distributed systems. But I don't think that there are a replacement for a poor design. So if you have a good decomposition of lowly coupled servers that you're able to deliver a highly available applications, then you optimize that with the caches at the right places and reduce the traffic a lot. But it's an afterthought in this way if you look at the functional design. So that's technical optimization, but it's not covering up for that this service or that this request needs to access 50 services because you just screwed up your design. That's a different story, basically.
But you could say even HTTP is poor design, so you cannot get away with this thing. So synchronous calls are poor design, and this is a de facto standard on the internet and in the mindset of the developers, simply.
Again, HTTP is a solution for a specific use case. And in this use case, the caches at the right places make sense. Usually also at HTTP in the original way wasn't designed for having long call chains. So it's different. I'm talking about microservice design where you end up with long call chains and other things. And so that you think in terms of reusability, that you have this ideas like, I design a system and here I've got a customer service and here's the offer service and here's the contract service, and I can't do anything with the contract service without the customer service being available because I can't display a single line of code. And that's where I think that caches don't really help in the end. I mean, they can be some kind of relief, like a faster CPU, but they are not a cure for the original problem. So if you just want to use technology or technical solutions for covering up that you're not able to design, I think it's not my way, at least.
Presentation.
Microphone. The other microphone.
Okay, thank you for a very good and inspiring presentation. I would like to share that with my colleagues from my team. Will that presentation will be available somewhere?
Yeah, sure. I think the organizers will distribute it. The talk will also be made available via its Vimeo or YouTube, so you will find that on the website. And I will also release that today on my SlideShare account. So you have lots of options to pick that slides up.
Yeah. So all except for those talks where the speakers don't agree to have it taped, everything will be taped and it's going to be on YouTube. We are aiming to have that in the next few days on YouTube.
Hi, I just wondered if you had any advice or ideas for actually modeling these massive distributed systems, because we're in a position where explosive growth has caused actually no one in the organization to even understand the whole system as a whole, and that's a problem that we're trying to solve, basically.
Indeed, it's a challenge, but the longer I deal with distributed systems, the more I'm convinced that you shouldn't even try to understand the system as a whole. It's the same way as you are never trying to understand a complex organization as a whole. You just need to know where to dive in, and you just have to make sure that there are ways, easy ways, that a new player, so a new service, can get into the play, can deliver its service, and make the results available to other places. So this central coordination idea, which we hold very dear, is dissolving. So as in real life, I always say control is an illusion, which makes you free to act. And it's also in distributed systems a little bit similar like that. So at least that's where my mind shift is, or my mindset is going to get towards.
So thanks a lot for the presentation again. So we are going to have a coffee break downstairs until 5 minutes past 11. So see you here.